I put this short quiz together so you can see if you're ready for the in-class quiz over Chapter 15, Equilibrium, tomorrow. So all of the questions are listed on this first page, and they are all related to this reaction. Okay, and assume when answering any of the questions that it's a STP conditions and that Kc is 2.4 times 10 to the minus 9. Oh, whoops, yeah, and delta H is minus 37.5 kilojoules per mole. So these are the four questions. The first one is Le Chatelier, as is the second one. The third one is solving for K, because what we've been given is, or solving for Kp, because what we've been given is Kc. And the last one is testing your expertise at ice tables. So this is what I recommend doing. I recommend not moving on, like putting this video on pause, not going to the next page, and trying to solve each one of these on your own first, and then check your answers. And if you have trouble, I'll try to explain them all pretty carefully. All right, so I just rewrote the reaction at the top of every page. So the first question is a Le Chatelier question. It says, if volume is decreased, what will happen? How will the system respond? Well, you first have to decide what effect a change in volume will have on pressure. And then you have to remember that if volume is going down, so imagine squeezing a marshmallow, pressure must be going up. So this is what you have done to the system to bother the equilibrium. Okay, you have reduced the volume, which has caused pressure to increase. All right, so in response to what you have done, Le Chatelier is going to want to undo or do the opposite of what you have done. Since you have caused a pressure increase, Le Chatelier will attempt to decrease pressure. Okay, so the only thing Le Chatelier has in its control is to shift a reaction either right or left. That's the only thing it can do to adjust. So how is this reaction going to decrease pressure? Pressure comes from collision of gas molecules against the container. So the more gas molecules you have, the higher the pressure. So to find out which way it'll shift, you count gas molecules on either side of the arrow. On the product side, you have 2 gas molecules. On the reactant side, you only have 1 gas molecule. So if a system wants to decrease or lower pressure, it's going to shift to the side with fewer gas molecules, and that means it's going to shift left because there's only 1 gas molecule here. Okay, so you would say the reaction will shift to the left or towards reactant in response to a decrease in volume. The second question I asked is another Le Chatelier problem, and it asks about changing heat. Anytime you have a Le Chatelier question that mentions heat, you first need to find out or be told whether this reaction is exothermic or endothermic. In the beginning, I gave you the delta H, enthalpy of reaction, and I said it had a negative value. Negative delta H values are always exothermic, and if a reaction is exothermic, you treat heat as a product. So I always rewrite the reaction, and I literally write in the word heat where it belongs, in this case as a product. If it's endothermic, you would write it over in the reactant part. All right, so now just treat heat like any other product. So this question said if the system is cooled. If you cool a system, that is like lowering or removing heat. So imagine standing there and pulling heat out. How is Le Chatelier going to respond? Well, Le Chatelet wants to do the opposite of what you're doing. So if you're removing heat, Le Chatelet wants to make more heat to replace what you've taken away, which means it will shift right, okay, so that more heat is produced. This third question is a calculation, and this is where you will need to use the equation that converts Kp, interconverts Kp and Kc. It's simply the equilibrium concentration in terms of pressure versus the equilibrium concentration in terms of concentration, or molarities typically. So this is the equation. R is the universal gas constant, and in this case, as in most gas problems, we're going to use 0.0821 liters, atmospheres, moles, Kelvin. Okay. All gas laws, or anything to do with gases actually, temperature must be in Kelvin. All right. And if you remember on the first page, I said everything to do with this problem is under STP conditions, standard temperature and pressure. Standard temperature is 0 degrees Celsius, which equals 273 Kelvin. Standard pressure is 1 atmosphere, or 760 torr. So now it's just a matter of plugging and chugging. We were given Kc in the problem, 2.4 times 10 to the minus 9. R value and standard temperature, 273 Kelvin. Now this little guy, delta N, in the reaction, in case you missed class or don't quite understand what that is, delta N is the difference in the number of moles of gas on the product side versus the reactant side. So in other words, you literally count the number of moles of gas on the product side. So go to the product side, there are 2 moles of gas, so that's 2, okay, minus number of moles of gas on the reactant side. This is a solid, so it's not going to count, and we have 1 mole of gas on the reactant side. So 2 minus 1 is 1. So our delta N value is 1. So, all right, so if you plug that into your calculator, you get that Kp is 5.4 times 10 to the minus 8. So here is the ice table. The first off, I rewrote the reaction we're starting with, and I always like to write that at the top of my ice table. And notice, I picked this one on purpose because if there's a pure solid or pure liquid, you're just going to put an X through the ice table because it's not going to affect your equilibrium. The only information we were given in this problem is that the initial I concentration of CO2, the other reactant, is 2. If you are not given a concentration for product, assume it's 0. We weren't given any other information other than K, so we weren't given any equilibrium concentration, so we have to use X in this ice table. So we know that the reactant is decreasing and that the product is increasing. So we're going to just call minus X for how much the reactant is decreasing. I'm just going to call it X. And looking at stoichiometry, for every 1 carbon dioxide that disappears, 2 carbon monoxides are formed. So the change for carbon monoxide is 2X, twice as much. It's going to change 2 times faster. And this C stands for change. Notice also that since the reactants are decreasing, there's a minus in front of my X. And for the product, carbon monoxide, the amounts are increasing. Obviously, we start at 0. They have to increase. So there's a plus here. And now you just have simple math problems. 2 minus X is the equilibrium concentration for carbon dioxide. And 2X plus 0, 2X, is the equilibrium concentration for carbon monoxide. Once you have expressions for the equilibrium, that's what E stands for, concentrations, plug them into the value for the equilibrium expression, So equilibrium expression for this reaction are, as always, products, which is carbon monoxide, raised to the exponent, that's the coefficient, so don't forget that, divided by reactants. So that's carbon dioxide. There's only a coefficient of 1 there, so you can leave it out. Now, notice I did not include the concentration of carbon in the K expression because it is a pure solid. So not only does it not affect the equilibrium, it's a constant itself, so it's not included over here with the variables. So we were given that Kc is 2.4 times 10 to the minus 9. So now it's plugging in your equilibrium values and solving for x, which I've shown on the next page. All right, so I just rewrote it. Here's Kc. And I plugged in equilibrium concentration values for products and reactants. So the carbon monoxide product was 2x, don't forget the square. And the carbon dioxide equilibrium concentration was 2 minus x. Now, on all of my quizzes and tests, you will always be able to neglect x. That won't be the case. There may be a bonus problem on the test where you cannot neglect x. There are always 1 to 2 problems on the ACS final where you cannot neglect x. If you were to keep x in this equation, you would end up needing to use a quadratic formula. So if you want a chance at getting one of the possible bonuses and or if you want to be able to answer those questions on the ACS final, I would recommend practicing at least a couple of these ICE problems where you have to use a quadratic. So let me explain, because I might well ask this on your final, not on your final, on your next exam. When is it safe to neglect x? The first thing you want to do is look at the value for k. If k is very small, and this is really small, okay, to the negative 9, that means not very much product is going to form. So if k is small, that in turn means that x is very small. Okay? And if x is small, it's okay to neglect. That means it's a lot smaller than the amount you're subtracting it from, which is 2. So if x is on the order of 10 to the minus 9, it's trivial compared to 2. So we're just going to cross out this x and solve it without that. Here's the Kc value again, okay? And now if you square 2x, you get 4x squared. Don't forget to square the 2 inside the parentheses too. A lot of students forget to do that. All right, and so now in the denominator, instead of 2 minus x, we simply have 2. That simplifies to 2x squared. So now we have 2x squared equals 2.4 times 10 to the minus 9. I'm trying to get x by itself on one side of the equation, so I divided both sides by 2. And when I do that, I get 1.2 times 10 to the minus 9. And then I'm going to take the square root of both sides to get x. Okay, so now over here I'm taking the square root of 1.2 times 10 to the minus 9. And that is 3.5 times 10 to the minus 5th molar. Now, listen really carefully. A lot of students on a free response problem, and there will be an ICE table on your free response. A lot of students solve for x and like, I'm done. You know, x is the magic number. Not always, and in fact, probably not even most of the time. What is x? Go back to your ICE table and see what x is and see what the problem is actually asking for. If we will find that the problem is asking for equilibrium concentration of the product, carbon monoxide. And if you go back to your ICE table, the equilibrium concentration of carbon monoxide is 2x. So if you solve for x and think you're done, you have not answered the question, which is asking for the equilibrium concentration of carbon monoxide. That answer, 2x, 2 times the x value you just found. So the answer you're looking here is 7.0 times 10 to the minus 5. Now, all your other concentration values were molarity, so that's going to be your units Don't forget your units, please. That's it. You did pretty well on these questions. I would say you're in good shape for the in-class quiz tomorrow.